So let's look at an example of the chi-square two-way test for independence. Let's look at this example of religious affiliation and gender. So here's a basic table of counts or frequencies for our religious affiliation variable and our gender variable. This is just a contingency table. Right? You can see that we have 143 people who are women and Protestant, 75 people who are male and don't have a religious affiliation. This contingency table, it has 2 rows and 3 columns. So R is 2, C is 3, and the total sample size is 518. So if you add up all of those 6 counts, you'll get 518. We want to know, are these 2 variables, are they independent or dependent in the population? We just have a random sample of data, so we don't actually know what's going on in the population, but we're going to use this random sample and the knowledge of the fact that it's a random sample to really say something about the population, make a conclusion. So the preliminaries we've already checked in the sense that it is a random sample, right? It is a contingency table, and the expected cell counts are going to be larger than 5. That's just a reflection of the fact that the sample size is pretty large, right? This is, in general, if you have a larger sample size, you're not going to run into problems in terms of the preliminaries required for the two-way chi-square test for independence. So let's move on to steps 1 and 2. We are conducting a two-way chi-square test for independence, so our hypotheses are as follows. The null is that in the population, gender and religious affiliation are unrelated. They're independent. The alternative is that in the population, gender and religious affiliation are related. They are dependent on each other. By convention, we're going to set alpha to 0.05. Then for step 3, we can calculate the chi-square test statistic. Right? This is based on not only the observed counts, but the expected cell counts. These are the expected cell counts under the assumption that these 2 variables are not related. So the expected cell counts are simply the row totals times the column total divided by the overall total. So for example, in the upper left cell of our contingency table, right, we have the row total is 283, the column total is 247, and the overall total, the total sample size, is 518. So that expected cell count is 135 roughly. Okay? So looking at the upper left-hand corner, the expected cell counts, if religion and gender are not related, that is going to be 135. Again, it's just a function of the fact that we're taking the row total, so there are 283 females overall, and then we're finding the total number of people who are Protestant, which is 247, and the overall total, which is 518. So the idea is we're going to have 6 cell counts that reflect expected cell counts under the assumption that the 2 variables are not related to each other. Okay? Then based on these expected observed counts, we can compute the test statistic. Right? The chi-square test for independence is that it's just based on this test statistic where I is an index for the total number of cells. So in our case, we're going to have 6 cells. We're going to have I equals 1 to k equals 6, right? Because we have 2 times 3 equals 6 cells. So we can calculate this by hand, and I strongly encourage you to do so. All you're doing is you're taking the expected cell counts minus the observed cell counts, squaring it so it's positive, and dividing by the expected cell counts. And you're doing that for each cell. Right? So you're going to do this 6 times. You're going to have 6 terms. When you add all this up, you get this chi-square test statistic of 5.659. This is sort of a standardized measure of how consistent our data is with the null hypothesis. And this chi-square test statistic, it's plotted on a chi-square distribution model with degrees of freedom governed by the number of rows minus 1 times the number of columns minus 1. Once we've calculated the chi-square test statistic, we can compare this test statistic with a critical value or use this test statistic to compute a probability or p-value. So the critical value is that the idea being that if our chi-square test statistic is greater than or equal to the critical value, then we can reject the null of independence in the population. So setting alpha to 0.05, right, and using the degrees of freedom for this table, our critical value is 6. Okay? And in this case, since our test statistic is less than 6, we're going to fail to reject the null at the alpha 0.05 level. In this case, we failed to reject the null of independence, so we conclude that gender and religious affiliation are in fact not related to each other. You can also compare and calculate a p-value. So for the chi-squared test, the p-value is simply the probability of obtaining a chi-squared test statistic greater than or equal to the one we've obtained. So the p-value is that alpha, if we have a p-value less than alpha or equal to alpha, then we're going to reject the null hypothesis of independence. So in this case, the p-value is greater than 0.05, so we're going to fail to reject the null at the alpha of 0.05 level. Right, that area under the curve to the right of 5.65, to the right of or including 5.65, it's larger than 0.05, so we fail to reject the null hypothesis. Based on the critical value of the p-value, we can make a conclusion. Now, this is a statistical output using statistical software. They call it Pearsons Chisquare Test. This just refers to the fact that Carl Pearson, one of the founders of statistics, was influential in developing this test. The key point here is that just as before, okay, we are given the observed and expected cell counts, as well as some additional information, which I describe here. And we're also given the Chisquare Test statistic, which is what we can calculate by hand. We're also given the degrees of freedom, and we're also given a probability or p-value. Right? The probability value is just above 0.05, so we fail to reject the null. We don't have enough evidence, right? So in this case, we say, well, we think that these two variables are in fact unrelated, right, in the population. So we make a conclusion, right? These findings suggest there are no major religious differences between young men and young women in the population. Now, we might consider increasing the sample size or breaking down to more religious groups to really further our analysis. But at that point, we can say that we really have made a conclusion about the population using this random sample of data from that population.